This video will help you understand how to estimate average atomic mass and continue to our work on finding particles in atoms. So this note's topic is average atomic mass. So some quick questions here. Okay, so if we look at our periodic table and we ask what number in the element box have we not discussed as much? And the answer to that would be this one down here on the bottom, otherwise known as the average atomic mass. Now you'll notice that that has the word mass in it, okay? And so our question is, how do we go about getting the mass of an atom? Well, we already know the answer to that. In order to figure out the mass of the atom, we add protons plus neutrons. All right, so now if we take a look at boron on our periodic table, the square looks like this. We ask, what is the average atomic mass for boron? Well, the answer for that is 10.81. So the question then is, if we know that the mass of the atom is protons plus neutrons, can we get that mass, 10.81, by adding protons and neutrons? And if you're thinking about it, the answer should be no, because we can't have 0.81 of a proton or neutron. We can only have whole numbers. So the question then is, what is this average atomic mass then? Where does it come from? All right, so here's our definition. The average atomic mass is a weighted average of the natural abundance of all the isotopes of an element. Okay? And we measure it in a set of units called the atomic mass unit, or the AMU. Now you might be looking at this definition and going, say what? What does he mean by that? What is a weighted average? What do you mean by the natural abundance? Well, let's start with that. Let's start with isotopic abundance. What do we mean by that? Well, we mean the percent of all of the isotopes of an element that have a specific mass. So imagine that I took a strip of magnesium metal and I blew it up so that we could see all of the atoms that were in it and know their masses. What we would find, as we've seen before, is that most atoms have multiple isotopes. Some are more common than others, okay? So we're going to go ahead and I want you to look over here and I want you to look through the sample and think about which isotopes are present. What isotopes do you see represented in this diagram? Well, hopefully you saw magnesium 24, magnesium 26, and you probably also somewhere in here saw a magnesium 25. There it is. All right. So then the question becomes, how many of each of them are there? So now you just go through, count them up, see how many there are. And if we do that, we discover that we have 16 that are Mg24, 2 that are Mg26, and 2 that are Mg25. Okay? Or in other words, 80% of this is magnesium 24, 10% is magnesium 25, 10% is magnesium 26. Where did I get those percentages from? Through calculating them. So 16 out of 20 total gives me 80%, right? And so that's where we got that number from, times 100. All right, so now that we know what the isotopic abundance of each is, we can figure out which one has the greatest isotopic abundance. And that should be easy. We should very simply be able to see there's 16 of those. It's 80% magnesium 24. Which one has the lowest isotopic abundance? Well, that would be a tie. Both 25 and 26 are only 10% of the total mass. All right, so when we ask about isotopic abundance, this is what we're talking about. What percentage of the atoms within a sample, within a natural sample, are each of the different types of isotopes? Okay. The other thing that they talked about in that definition was that average atomic mass is a weighted average. And what do we mean by that? So a weighted average is an average that takes into account both the values of a measurement and the percent of items with that value. Okay. For elements, that weighted average is the average atomic mass. In the case of boron, 10.81. So how do we go about counting that? Well, if we wanted to calculate it, what we would do is basically we would take the percent abundance of each isotope as a decimal and multiply it by the mass. And we would do that for each isotope that we have, and then we would add up the results and we would get an average atomic mass. Okay, now we could do that, right? We could go 0.8 or 80% times 24 for this. We could go 10% times 25 for this, and 10% times 26. But in order for us to know that you really understand this, really what the best trick for us to do is for you to go ahead and make estimations. So how do we estimate the average atomic mass rather than just calculating it out? Well, here are the things we know. The average atomic mass is always going to be between the lowest isotope's mass and the highest isotope mass that we have. Okay, so it's going to be in between there. We also know that it's going to be within one of the isotope that is most common, that has the greatest abundance. And then we can adjust that one. Once we figure out that it's close to that one, we can make it either a little bigger or a little smaller than that, depending upon the mass and abundance of the other isotopes. Okay, so let me show you what we mean by this. Okay. Example number 1, we're going to estimate the atomic mass of an element called marbelium. This is a fake element. It doesn't really exist. Okay, so we're going to go through this, and we're going to go through this systematically. When you get better at this, you don't actually have to answer all of these questions, but to start off with, we will. So first thing we want to know is the range. What's the smallest value and the highest value that our average atomic mass should be in? So we start this by asking, what is the smallest mass of the marbelium isotopes? Okay, so again, mass. We're looking at the smallest mass. What's that going to be? Well, hopefully you see that it's 16, right? A mass of 16 is less than a mass of 19 or a mass of 20. Masses are written after the dash in there. Okay. What's the highest mass? Well, hopefully from looking at that should be easy as well, 19. Okay, so at this point we know that our atomic mass, or average atomic mass, is going to be somewhere between 16 and 19. Okay, now we can get it even closer than that by figuring out which isotope has the greatest abundance. Okay, so 60%, 35%, 5%, obviously it is this one. Okay, so we know that it's going to be between 16 and 19. Okay, and it's going to be very close to 19. Okay, well, that means that it's going to either be 19 or going to be a little bit less than that. Okay, so then we have to look at the other isotopes, and we have to look, are they going to make them, likely going to make the average atomic mass less than 19, greater than 19, and by how much, what are they going to do? So my other isotopes are 17 and 16. Those are obviously both smaller than 19. So we're going to estimate here that they're going to make the average mass less than 19. How much less? Well, plus or minus 1. Well, in this case, it would be minus 1. So we now know that our average atomic mass is going to be somewhere between 18 and 19. Okay. How much less is it going to be? Well, about 40% of the masses are less than 19, and 60% is more than 19. And they're 2 less and 3 less than that. So I'm going to say this is going to make a pretty significant impact here. I'm going to guess that it's going to be somewhere in the middle between 18 and 19, and so I'll go with a mass of 18.5. Okay. So a good estimate of that average atomic mass of marbelium is 18.5. Okay, and if we actually calculated it out, we would get 18.15. Okay, quite a bit less. Okay, so our estimate ended up being a little bit high at 18.5, but again, within range, not too far away. So 18.15, 18.5, those are pretty close to each other if we're just estimating. Okay, let's do one more. Let's do our magnesium from earlier. Okay, what is the lowest mass of magnesium we have? Well, again, these are the mass numbers, so our lowest mass is going to be 24. Okay. What is the highest mass of our magnesium isotopes? Well, obviously 26. So at this point, we know that this is going to be somewhere between 24 and 26 as an answer. What's in the greatest abundance? Magnesium is at 80%, so that is one that is most abundant, 24. Okay. Will the other isotopes likely decrease or increase the atomic mass? So 20, we know it's going to be somewhere close to 24. We know it's between 24 and 26. And we know that these ones are bigger, okay? 25 and 26 are bigger than 24. So we know that this thing is going to end up being greater than 24, okay? Not as big as 25, because 25 isn't most abundant, but it's got to be somewhat greater than 24, okay? These are 1 and 2 AMUs bigger than the 24. So 25 and 26 are 1 and 2 bigger, but they make up a really, really small amount of the total abundance. 10% is this and 10% is that. So I'm going to say it's probably just a little bit greater than 24. Okay, it's going to raise a little bit greater than 4. So a good estimate then, maybe like 24.3 would be a good one. Okay, less than half. What is it actually if we look at the period table? 24.31. Dang, that was a pretty good estimate in this particular case. Okay, so that's how we do estimating average atomic masses. Once we get good at it, it's much, much faster than trying to calculate, and it gets us close to, and it helps us understand where does the average atomic mass number come from. All right, one other thing besides being able to estimate average atomic mass that we need to know is we need to understand what we mean by this term, most common isotope. And this is simply the isotope that occurs most often in nature. For example, in our magnesium sample before, it was 80% magnesium-24. The other ones were only 10%. So what is the most common isotope? 24. It happens more than any of the others. It also is usually the isotope whose mass is closest to the average atomic mass, right? 24.31. What's closest to that in terms of a whole number? 24. So let's go ahead and let's do the most common isotope of boron. How do we find that? We look at the average atomic mass, which is 10.81. What whole number is that closest to? 11. So the most common isotope of boron is 11. Okay. You try xenon. Come back to the video when you've got an answer. Xenon's average atomic mass is 131.29. Okay, so what's a good guess for the most common isotope of that? Again, the whole number that's closest to 130.29, or xenon 131. Next one, lithium. Okay, lithium is on the periodic table. Go check it out. You'll find it has a mass of 6.94. What's whole number is that closest to? Lithium 7. Okay. Again, as we said over yesterday, as we were doing counting problems or counting particles, if no mass number is given and you can't get protons plus neutrons, you can assume you have the most common isotope and round that average atomic mass. All right, so now that you have that done, you can work on the average atomic mass assignment. Okay, the answers for it are posted in Schoology. And then once you're done and you feel like you know what you're doing, you can go ahead and take the average atomic mass quiz, also in Schoology.